Hello everyone, welcome to Brain Views. Today we will look at another important topic, Earth's atmosphere. Here we will talk about the layers of the atmosphere, their characteristics and temperature variations. What is atmosphere? The atmosphere of Earth is a layer of gases surrounding the planet Earth retained by Earth's gravity. These layers of gases protects the Earth from the radiations and cosmic rays coming from the outer space. The Earth's atmosphere plays several vital roles that sustain life and protect our planet. Acting as a protective barrier, it shields the surface from harmful solar radiation, cosmic rays, and even prevents most meteoroids from reaching the ground. It also regulates the climate by trapping heat through the greenhouse effect, which keeps Earth's temperature within the range suitable for life. Beyond protection and regulation, the atmosphere enables essential gas exchanges that support processes like photosynthesis and respiration, making it possible for plants, animals, and humans to survive. Moreover, it drives weather patterns and powers the water cycle, ensuring the continuous redistribution of water across the globe. The atmosphere is comprised of five main layers based on temperature. These layers are the troposphere, stratosphere, mesosphere, and thermosphere. A further region at about 800 kilometers above the Earth's surface is called the exosphere. The troposphere, whose name comes from the Greek word tropos, meaning change, is the lowest layer of Earth's atmosphere. It is called this because the weather is constantly shifting here, with winds and gases mixing continuously. This layer lies closest to the Earth's surface and extends upwards to about 12 to 18 kilometers on average. Containing nearly 75% of the atmosphere's air and most of its water vapor, the troposphere is the region where clouds form and rainfall occurs. It is also the layer where hot air balloons rise and float, staying well within the bounds of this dynamic part of the atmosphere. The stratosphere, derived from the word "strat", meaning layer, is the second major layer of Earth's atmosphere, lying just above the troposphere. The boundary between the two is called the tropopause, a region where airplanes commonly fly. The stratosphere itself stretches upward from the tropopause to about 50 kilometers above Earth's surface and is organized into its own distinct layers. One of the most important features of this region is the ozone layer, a thin band of ozone molecules located approximately 15 to 30 kilometers above the ground. Although the concentration of ozone here is less than 10 ppm, it plays a crucial role in absorbing 97 to 99% of the sun's harmful ultraviolet radiation. Without this protective shield, UV radiation could cause severe damage, such as disrupting DNA in skin cells, leading to genetic mutations, skin cancer, and premature aging. In the atmosphere as a whole, ozone accounts for only about 0.3 ppm, yet its presence in the stratosphere is vital for life on Earth. Interestingly, ozone molecules are constantly being created and destroyed in this layer, but the overall balance has remained relatively stable over time. The stratosphere is also important for scientific research. High-altitude weather balloons, known as radio sondes, are released into this region to monitor atmospheric and climatic conditions. These balloons, filled with hydrogen or helium, carry small instrument packages that measure and transmit data on altitude, pressure, temperature, relative humidity, wind speed, wind direction, cosmic rays, and even geographical position. This information is sent back via radio signals to ground receivers, providing valuable insights for weather forecasting and climate studies. The mesosphere, whose name comes from the word meso, meaning middle, is the layer of the atmosphere that lies above the stratosphere and below the thermosphere. It is about 35 kilometers thick and is separated from the stratosphere by the stratopause, the transition boundary between the two layers. This region is particularly important because it is where most meteors entering Earth's atmosphere burn up, creating the bright streaks we see as shooting stars. Additionally, meteorological rockets are often sent into the mesosphere to carry out upper air observations, providing valuable data for atmospheric research. The thermosphere, derived from the word "thermo", meaning heat, is the atmospheric layer found above the mesosphere and below the exosphere. It begins at the mesopause, the coldest region of Earth's atmosphere, and extends upward to about 800 kilometers above the planet's surface. This makes it the thickest layer of the atmosphere. Despite its extremely high temperatures, the air here is very thin, consisting mostly of the lightest gases such as oxygen, helium, and hydrogen. The thermosphere is also home to fascinating natural and technological phenomena. It is the region where dazzling auroras light up the sky and where most satellites orbit the Earth. The exosphere, named from the word "exo", meaning outside, is the outermost layer of Earth's atmosphere. It stretches from the upper boundary of the thermosphere out to around 10,000 kilometers above the Earth's surface. In this region, the air is extremely thin, and atoms and molecules often escape into outer space. The exosphere also serves as the zone where spacecraft travel and where high-altitude satellites orbit our planet, marking the gradual transition between Earth's atmosphere and the space. The ionosphere, named from the word "iono", meaning ions, is a region of the atmosphere rich in electrically charged atoms and molecules. High-energy solar radiation, such as extreme ultraviolet and X-rays, ionizes these particles, creating layers filled with free electrons. Unlike other atmospheric layers, the ionosphere is not a distinct single layer, but rather a series of overlapping regions found within the parts of the mesosphere and the thermosphere. It plays a vital role in communication and navigation by reflecting and modifying radio waves, allowing long-distance transmission. The ionosphere is divided into three main regions known as the D, E, and F layers, although these do not have sharp boundaries. Instead, their altitudes shift depending on the time of the day, solar activity, and even the season. In the troposphere, the temperature near Earth's surface averages about 15 degrees Celsius, but gradually decreases with altitude, reaching nearly -56 degrees Celsius at the tropopause. This cooling follows the environmental lapse rate of about 6.5 degrees Celsius per kilometer. The sun's radiant energy passes through the atmosphere and warms the Earth's surface, which then transfers heat back into the air by conduction and convection. As warm air rises, it expands due to lower pressure at higher altitudes. This expansion requires energy drawn from the heat of the air itself, a process known as adiabatic cooling. As a result, rising air becomes progressively cooler with height. Additionally, because gas density decreases with altitude, the air absorbs very little incoming solar radiation, reinforcing the cooling trend. In the stratosphere, conditions shift dramatically. Just below the ozone layer, temperatures remain relatively constant, but above it they begin to rise steadily, reaching about -2 degrees Celsius at higher levels. This warming occurs because ozone molecules absorb ultraviolet radiation, particularly the more harmful UVB and UVC rays, and convert that energy into heat. The higher the altitude, the more solar radiation is absorbed, so the temperature increases with height. The stratosphere is also very dry, and clouds are rare in this region. Moving upward into the mesosphere, the temperature begins to fall again, dropping from about -2 degrees Celsius near the lower boundary to as low as -86 degrees Celsius or even colder near the upper limit. This makes the mesosphere the coldest part of the atmosphere. The low density of air molecules means little heat is absorbed, and with no ozone layer to trap thermal energy, cooling dominates. Carbon dioxide also contributes by absorbing heat during molecular collisions and releasing it as photons through radiative cooling, effectively carrying energy away. In fact, the extreme cold of the mesosphere is sufficient to freeze water vapor into thin ice clouds. Above this, the thermosphere experiences a dramatic rise in temperature, climbing from about -86 degrees Celsius at its base to well over 1000 degrees Celsius near the top. Despite these high readings, the air pressure here is extremely low, with only sparse molecules of oxygen, helium, and hydrogen spread far apart. These molecules absorb intense solar radiation, including ultraviolet light, X-rays, and gamma rays, becoming superheated. However, because collisions between molecules are rare, very little actual heat is transferred. This means that while instruments may record extremely high temperatures, the atmosphere would feel cold to human observers. In the exosphere, the relationship between temperature and height is very different from the pattern seen in other layers of the atmosphere. This region is almost like a vacuum, with air so thin that molecules are extremely sparse and collisions between them are rare. Because of this low density and pressure, heat transfer is minimal, even if the few particles present are moving at very high speeds. As a result, the exosphere can record extremely high temperatures ranging from near zero up to more than 1700 degrees Celsius, primarily due to the absorption of intense solar radiation, especially ultraviolet and X-rays. However, despite these high readings, the lack of molecular collisions means there is almost no sensation of heat, making the exosphere feel extremely cold to humans or instruments placed there. Here is an extra detail for you. In the stratosphere, the temperature pattern is quite different from that of the troposphere. Instead of cooling with altitude, the air actually becomes warmer as you go higher. This phenomenon, known as a temperature inversion, occurs because the ozone layer absorbs ultraviolet radiation from the sun and converts it into heat. The warming effect creates a stable atmospheric layer with very little turbulence and limited vertical mixing. As a result, gases and particles that enter the stratosphere can remain there for long periods of time, making this inversion one of the most distinctive features of the stratosphere. That is it for today's video. Don't forget to subscribe to Brain Waves and like and share this video. See you again in another interesting topic.